퀴즈 2번 봤죠? So what my plan is have a quiz next week. May 15. It's again 1 hour quiz with this is next week, 1 hour. So you can prepare 1-page sheeting sheet. And May 22nd it's a compensation week. 보강 주간. I'm going to have a class because last week was a holiday, so we didn't. Not holiday, right? The Equidimensional, the anniversary of the university's foundation day. So I'm planning to have a class on 보강 주간. So hope there is no confusion about that. So previously we covered how to solve the first order differential equations with the logarithmic derivatives, right? The first order ordinary differential equation is actually a problem of finding the logarithmic derivative. So next quiz will be maybe half of the topics is about this, and also I asked you to check those logarithmic derivatives in CLC handbook, right? I gave you about how many, 50 or so, and also I asked you to check the derivative, maybe 10 of them during the break. So I guess you will be in a good position to handle those the first order ordinary differential equations. And starting today, we are going to spend more systematic study of ordinary differential equations. So we are going to focus on nth order linear ordinary differential equation, which is of the following form: a0x txn tn yx a1x txn minus 1 dn minus 1 yx blah 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 anx yx is qx. So that is a general nth order linear ordinary differential equation that we are going to study during this semester. And depending on whether qx is 0 or not, it is called homogeneous or inhomogeneous. So when qx is 0, it's called homogeneous nth order linear ODE. When qx is non-zero, it's called inhomogeneous nth order linear ODE. So between two, which one would be easier? Less difficult, I mean. I wouldn't say easier. case of qx is 0 or qx is non-zero? Which one would be less difficult of those two? Obvious, right? The first case would be easier than non-zero case. So we will be focusing on first. Also, we will consider the case when all these A0x, A1x, ANX are called coefficient. And the most simplest case of coefficients are they are all constant, right? So let's study the case of the simplest case, the constant coefficient. Case 1. And also, of course, n homogeneous. So the differential equation is dxn So the differential equation form is substantially simplified because the A0, A1, and AN are all constant. And also, of course, the source term Qx is 0, so it's a homogeneous, ordinary linear differential equation with the constant coefficient. So A0, A1, AN constant. How many of you have taken 수능? So most of you taken 수능, right? Maybe half of you. And okay, they have math. And okay, there is a difficult problem. You cannot find the answer. What do you do? Maybe I can rephrase in, okay, there is some mathematical problems, which is a bit difficult, and you don't know the answer, so what do you do? Okay, like in my quiz, if there's a penalty, you just give up, right? It's better than getting a wrong answer because you get minus. But if there is no penalty, what do you do? Right. You 찍어요, 그죠? Right? Actually, there is a more better expression, is educated guess. Educated guess means 읽는다. So what you can try in this case, we can try trial solution and see what happens. Such as y exponential lambda x. So we can try a trial solution of exponential lambda x. 찍어요. Making an educated guess. So making an educated guess. 찍는다. It's not a good expression. Maybe I can 추측한다. A bit more sophisticated, right? 추측한다. So let's try to educate the guess. And what is the exponential lambda x? We can make a chain rule, right? So set lambda x as g, then dx exponential g is dg d exponential d dx dg, right? So that is, if we differentiate exponential g by g, it doesn't change. However, dx dg is lambda. So this is lambda exponential lambda x. That's the beauty of this exponential function. I don't know why we are having better. Not better. So maybe I should put it here. Maybe something better. Right. So maybe something with the position of a microphone. So we can say dx t exponential lambda x is lambda exponential lambda x. How about if we differentiate twice? It's lambda square exponential lambda x, right? So you can continue this process until so as a trial solution, A0 dx n dn exponential lambda x plus A1 dx n minus 1 A0 exponential lambda x is A0 lambda n A1 lambda n minus 1 A0 exponential lambda x is equal to 0, right? But if we are considering the when lambda is real, exponential lambda x is never 0, right? So only possibility is A0 lambda n, A1 lambda n minus 1, A0 is equal to 0. So this is simply the algebraic equation. So an algebraic equation can be solved in principle. So that's very simple. So the case of nth order linear ODE can be transformed into nth degree algebraic equation by setting y equal lambda x. That's a trick. So let's consider simple second order differential equation. So can I move on? Is my handwriting fast? Okay. How about my speed, my talking? My speaking is not fast, but my handwriting is fast. Yeah, so this is probably, differential equation is probably difficult subject for you. So I try to go slow as much as possible. And so one of the way to going slow is study possibly many examples. So study some examples. So for example, so this belongs to the case of linear constant coefficient, second order ordinary differential equation. And how many of you are taking circuit theory? 전기회로 듣는 사람. So maybe you have covered this RLC circuit. So for example, so current flow along the RLC circuit can be represented. Okay, we have a QX. Well, in circuit theory, we are talking about time. But anyway, so this linear differential equation for second order ODE is can be like represented by the circuit. Anyway, so if you say try lambda x, then we have lambda square plus 3 lambda plus 2 exponential lambda x is equal to 0, right? So we can factorize so lambda can be minus 1, minus 2. So that means exponential minus x and exponential minus 2x are solutions. But also, the linear combination is also solution. Also, c1 exponential minus x plus c2 exponential minus 2x is a linear combination. Is also solution. Because our differential equation is ordinary differential equation. So they are also the solution. So we can check. This is 2. So what is dx? d c1 exponential lambda x c2 exponential minus 2x. That is minus c1 exponential minus x minus 2c2 exponential minus 2x, right? And if we differentiate twice, minus x plus c2 exponential minus 2x is actually you differentiate x once again, so minus become plus. So that is c1 exponential minus x plus In this case, we have minus 2 and also another minus 2 from here. So it's going to be 4 c2 exponential minus x. So let's try to check dx squared, d squared, c1 exponential minus x, c2 exponential minus 2x, plus 3 times dx d, c1 exponential minus x, c2 exponential minus 2x, plus 2 c1 exponential minus x, c2 minus exponential 2x is c1 exponential minus x plus 4c2 exponential minus x. And 3, so minus 3c1 exponential minus x minus 6c2, exponential minus 2x plus 2c1 exponential minus x plus 2c2 exponential minus 2x. So let's check the coefficient for the exponential minus x. c1 minus 3c1 plus 2c1 is 0, right? How about minus 2x? c2, 4c2 minus 6c2 plus 2c2 is 0, right? So you can see that each is a solution, each exponential minus x and minus 2x is also solution, but they are linear combination. c1 exponential minus x plus c2 exponential minus 2x is also solution. That's because of the original differential equation is linear. Too many things, too many equations in one page, right? Maybe I should put some numbers so you cannot be confused. 3, 4. So we know, so most general solution is the linear combination of these two. So the most general solution is, I know I'm writing very fast. Exponential minus x plus exponential and 2x. So that we are going to call this homogeneous solution, c1 exponential minus x plus c2 exponential minus 2x. And there are two ways to determine this coefficient. So we have two unknown, c1 and c2, so we have to apply two conditions. One is initial condition. For this YH is 0, dx dyh 0 is 1. For example, this is just arbitrary, for example. Then YH 0 is C1 plus C2, right? Is 0. C2 is minus C1. Dx dyh 0 is minus C1 minus 2C2 is equal to 1. Or you can put this into this. Then C1 is equal to 1, right? And C2 is minus 1. So in this case, So yhx exponential minus x minus exponential minus 2x. That's the solution that satisfies the initial condition. Another condition is you apply the boundary condition. 2 different points. It's called initial condition. Or cause condition. Another possibility is apply a boundary condition. Say y0 is 0, y1 is 1. This is arbitrary condition, so I just put this way. So this is again arbitrary example. Then yh x is c1 exponential minus x, c2 exponential minus 2x, right? So yh0 is c1 plus c2 is 0, c2 is minus c1, yh1 c1 exponential minus 1, c2 exponential minus 2 is 1. So c2 is minus c1, so c1 exponential minus 1 minus 2 is 1. So c1 is e minus 1 minus e minus 2, c2 is minus e minus 1 minus e minus 2. So when the ordinary differential equations are given and solved, there can be 2 possible conditions to set the undetermined coefficient. One is initial condition. Another one is boundary condition. So you supply the boundaries. But mostly in circuit theory, it's initial condition, right? For our electronics or electrical engineering, most of the problems are of the initial condition type. But other branches like chemical engineering or mechanical engineering can be both boundaries and boundary conditions as well as initial conditions. Need to make a copy. So don't forget, next week we have a quiz. And second we have a class. Another case. So previously we considered lambda is a real number. What about this? So we can also try exponential lambda x. Then lambda squared plus 1 is 0. So there is no real number, right? So lambda is not real. So say lambda is I. called imaginary number because it exists only in our imagine, and it was discovered in 17th century, I think. Who discovered those imaginary numbers? This imaginary number is not quite clear. There is a rumor that Christian Euler discovered that, but anyway. So lambda square minus 1 so we can try exponential ix is a solution, right? If we substitute as before, then exponential ix or exponential minus ix is a solution. But what is exponential? How do you express the exponential with I in the exponential? There is Euler's formula. Exponential ix is cosine x plus I sin x. And exponential minus ix is cosine x minus I sin x. It's actually the topic of for the second semester, but so this can be actually shown by using Taylor's formula. You must have learned in your freshman video product. That is exponential lambda x is 1 plus lambda x plus 2 factorial lambda x square, 3 factorial lambda x cube, 4 factorial lambda x fourth. Anybody remembers this formula? You must have learned in freshman video now. And sin x minus x cube over 3 factorial 5 factorial of x fifths minus cosine x is 1 minus x squared over 2 4 factorial x4, right? So those are the formula that you learned in freshman calculus. So we can substitute exponential ix is 1 plus ix plus 2 factorial ix squared, 3 factorial ix cube, 4 factorial ix fourth. So it becomes 1 plus ix, I square is minus 1, right? So minus 2 factorial x squared minus 3 factorial ix cube and plus 4 factorial x to the 4, blah, blah, blah. So one can put into 1 minus x squared over 2 factorial plus x4 over 4 factorial minus plus, you can put I as a common factor, x minus x cube over 3 factorial, right? So So if you expand the exponential ix by Taylor series using this formula, then what is this? 1 minus, this is cosine, right? This is sine. So need time to copy. So in this case, exponential ix, exponential minus ix is also solutions, and so is linear combination 2I over exponential are also solutions. I mean, we have seen that previously. If each are solutions, then their combination is also solution, right? So for this differential equation, that our differential equation is this: dx squared d squared y plus y equals 0. This is a differential equation, and this exponential ix and minus ix are solutions of this equation. Then, according to our previous experience, that their combination is also solution, right? So I'm going to take one particular combination, exponential ix plus exponential minus ix divided by 2. It must be a solution. I think maybe running on the battery. And also possibly exponential ix minus ix divided by 2I are also solutions. So let's find out what are those. So exponential ix is cosine x plus I sine x. Exponential minus ix is cosine x minus I sine x. So if you add them together, what do you get? Two cosine x, right? So from this, 2 over exponential ix is a cosine x. The subtraction, maybe I can use this space. Exponential ix minus ix is 2I sine x. So 2I exponential ix minus ix is the sine x. So from this we can see that cosine x and sine x are also solutions of right? So because cosine and sine are much easier to handle than exponential minus ix and minus ix minus ix. So we can use those as elementary solutions and then combine them together for general solutions. So general solution can be C1 cosine x, C2 sine x. That's easier to handle, right? So for example, another example. Maybe 9y equal to 0. So the equation for lambda is lambda squared plus 9 is 0. So lambda is plus minus 3i. So we can see that cosine 3x, sine 3x are solutions, right? So general solution can be C1 cosine 3x, C2 sine 3x. And maybe we can try to solve for initial conditions. Okay, I will let you choose the coefficient. So what do you like to put? 0. Any number, you just name it. 1? Okay. How about YH? First order derivative? 1, 2. Okay. Like maybe I'll. That's okay. So YH0 is C1. What is sine 3, 0? 0, right? So C1 is actually 1. Oh, very nice choice. And if we differentiate, we have 3 minus C1 sine 3x, 3C2 cosine 3x, right? So dx dy hx x equal to 0 is obviously sine is 0. So we have 3C2, which is 2. So C2 is 2 over 3. So general solution is the following. YHX is cosine 3x plus 2 over 3 sine 3x. Nice. Since it looks like I'm going too fast, maybe we can take a break for 5 minutes. So, another example is this. Dx squared d squared y e 2 dx dy plus maybe 2y. So if we set this lambda x as trial solution, then we have lambda squared 2 lambda plus 2 is equal to 0, right? Or lambda plus 1 squared plus 1 is 0. Possible solutions, lambda plus 1 is plus minus I. So lambda can be minus 1 plus I, lambda 2, minus 1 minus I. So in this case, exponential minus x cosine x and the exponential minus x sine x is a solution. And C1 and C1 exponential minus x cosine x plus C2 exponential minus x sine x is all solution. So let's take some detour. Detour means 샛길. We call this a differential operator. Linear. Or LDO. So L act on a function yx and changes into something else. So for example, L yx. So L is an operator, which is something that acts on the function yx and changes that into something else. So which is a0 dx and dny a and y. This is a linear operator, means L C1 y1x C2 y2x A0, it operates on C1 y1 C2 y2 AN C1 y1 C2 y2 and it becomes C1. You can combine C1 as a 0 dx and dn y1 an y1 plus C2 a0 dx and dn y2 an y2, and it becomes C1 L y1x C2L y2x. Right. So if we add some functions together and then apply this differential operator, then the result is sum of each operand, each function, that part. So if you apply this, this L is a differential operator, which is something that acts on function yx and changes into something else. So if you apply this L to C1 y1 plus C2 y2, then the result is actually the combination of C1 and L acting on y1 plus C2 with the L acting on y2. So this property is called linearity. And so this topic can be a little bit difficult for you to understand because you never learned about the operator. Then the differential equation is actually the nth order linear ODE, which is A0 dx n tn y plus a n y is equal to 0, can be written as simply operator 0. Then there is interesting properties of operator, that L is given by A0, AN, A1, AN, LY, A01. Then, if we differentiate by something different, say lambda x, if we differentiate by lambda, what happens? Or say d lambda. We covered something about the partial derivative, right? So that is partial lambda partial A0 dx n tn y A1 dx n minus 1 tn minus y an y. And lambda and x are independent, you can change the order. So this is A0 dx n tn lambda y A1 dx n minus 1 tn minus 1 lambda y an lambda y. So this is same as actually L lambda yx. So partial lambda partial L yx the same as L partial lambda partial yx. It looks obvious, right? Lambda is independent variable from x. From x. And you may be curious why we are doing this, right? And that is, we're going to see why I'm doing that. Okay. All right. So it's time to come. Okay, so if then right. So the partial derivative can be put into the parentheses, the brace. So for example, we have following differential equations. Dx squared d squared y plus 2dx dy plus y equal to 0. Then, if you have a trial function over this, then you have lambda squared plus 2 lambda plus 1 is equal to 0, right? So lambda plus 1 squared equal to 0. So lambda is minus 1, minus 1. So in this case, we have only one root, right? It's called double root. But it is a second order differential equation, so we are supposed to have two independent solutions. So what can be the second one? Can be actually found from that operator property. So set dx squared plus d squared 2dx d plus 1. Then our differential equation is the following. L exponential lambda x equal to 0, right? If we differentiate by lambda, then partial lambda partial L partial lambda partial exponential lambda x is what is, if we differentiate 0 by lambda, what do you get? Again, 0, right? So look at this part. That means partial lambda partial exponential lambda x is also a solution, right? If L is 0. And from this property, because we know this is a solution because L, if you apply L by this function, is 0, right? So that's the solution of the ordinary differential equation. Then, from this property, this equation, that the L is operating on this function gives a 0. That means this is also solution. So, but x exponential lambda x, right? So we can check. Using this operator property, you can see that the partial derivative of exponential lambda x by lambda is also solution because this is 0, right? The differential equation is actually this. This is a differential equation, right? This is a differential equation. So that means lambda x is a solution. Then same way, that is also solution. Or I can say, more systematically, I can say it this way. This means right? So exponential L applied on exponential lambda x is equal to 0 means this is a solution of ODE described by L, right? By same logic, means it's a solution of ODE described by L. So let's check. So L is dx square 2dx d 1, right? So check L x exponential x minus 6. And let's check first. Dx d x exponential minus x is, you differentiate the first part, exponential minus x minus x exponential minus x, right? If we differentiate twice, minus exponential minus x plus x exponential minus x minus exponential minus x. So combine them together. So dx x exponential minus x plus 2 dx dx exponential minus x plus x exponential minus x is minus exponential minus x plus x exponential minus x minus x plus exponential, this is 2, right? X exponential minus x. So let's check. So this cancels each other. 2 cancels each other, right? So this is 0. So when we have a double root, then obviously we can see that more systematically we can also do following. If you still need time. I think I'm going a little bit too fast. So I try to slow down as much as possible. Okay, so starting with this dx square d square 2 dx d plus 1. So L actually is lambda plus 1 square lambda x, right? That's true, right? So if we substitute lambda x minus 1 is 0, right? And so is this. If you differentiate this twice, so lambda plus 1 square equals lambda x plus lambda plus 1 square lambda exponential lambda x is again 0, right? So that means x exponential minus x is also a solution. This can be obtained by this lambda exponential lambda x, lambda equal minus 1 is actually x minus x, right? So we can consider another differential operator. Another example. L is t cubed 3 dxt 3 dxt plus 1. So if we apply lambda x, what do we get? Lambda cube, 3 lambda square, 3 lambda plus 1 exponential lambda x, right? So it's lambda plus 1 to the cube exponential lambda x. So obviously it's a triple root. When lambda equals minus 1, both sides are 0, right? So when set lambda equal to minus 1 is lambda plus 1 cube is 0, right? So that means exponential lambda x is a solution. And what about derivative? So partial lambda partial L is actually L partial lambda partial both sides are 3 times of lambda plus 1 square exponential lambda x plus lambda plus 1 are 0, right? So exponential lambda x partial lambda partial is also a solution, which is x exponential minus x, right? And then you can differentiate twice. Can I move on? I think I'm still going fast. I don't know how to slow down. So let's say L y lambda exponential lambda x lambda plus 1 to the exponential lambda x, right? So if we differentiate twice, partial lambda partial L partial lambda partial exponential lambda x is lambda plus 1 cube 3 times lambda x plus lambda plus 1 cube lambda x. we can differentiate both sides again. Partial lambda square L partial lambda square exponential lambda x is 6 times lambda plus 1 exponential lambda x, 3 lambda plus 1 cube square exponential lambda x plus, this is tricky, lambda plus 1 cube exponential lambda x plus 3 lambda x plus 1 square exponential lambda x plus lambda square, this is lambda plus 1 cube exponential lambda x. So it's obvious, if you substitute lambda equal to minus 1, what do you get? When lambda becomes minus 1, this is 0, right? This is 0, this is 0, this is 0, 0, right? So, zero, right? That means solution. It's getting complicated. So for this equation, this is ordinary differential equation y. Then exponential minus x exponential minus x square minus x are solutions. So if they have case double root, if something like lambda plus 0k if say if we have a case root for lambda equal lambda 1, then obviously zero, right? So exponential lambda 1x is a solution. You can do this k minus 1 is again 0. So x to the k minus 1 exponential lambda 1x is a solution. So we can find the general solutions. We have a double root, triple root, quadruple root, etc., etc., etc. So I'm going to ask you to check the following as homework. So this is the properties of multiple root. So let's go back to the example. So we have some difficulty following me, right? So say, let's use color. Three dx squared d squared 3 dxt 1. And so we have a third order ODE, L 제곱 y 1 y equal to 0. Then show that x squared exponential minus x is a solution of above ODE. I'll give us homework. It'll take around maybe 10 minutes. And do you remember any this formula d to the 4? It's supposed to be 4, right? 6, 4, 1, right? Then L exponential lambda x is actually lambda 4, 4 lambda cube, 6 lambda square, 4 lambda plus 1 exponential lambda x, right? So can you factorize this in Sukunen? Lambda plus 1 to the 4, right? 2. Lambda plus 1 to the 4th exponential lambda x. So you can guess the solutions, right? So y equal to exponential minus x, x exponential minus x, x squared minus x, x cubed exponential minus x, right? So I will give you homework that show that x exponential minus x, x squared exponential minus x, x cubed exponential minus x are solutions of this differential equation dx 4y 4 dx 3 d3y 6 dx squared d squared y 4 dx dy plus y equal to 0. It could be fun, right? So maybe 30 minutes. Maybe a little longer because you have to differentiate 4 times. Half an hour, I would say. It's good homework. And we'll be in a good shape for next quiz. Maybe I can do more. What is 1 plus 5? Anybody remembers this formula? Binary expansion. 1, 5, 4, right? No, lambda 4, lambda 3, 5, 3, lambda square, 5, 2, lambda, this is 5, 4, 3, 2, 5, 1, lambda plus 1. So that's lambda to the 5 factorial, so this is 4 factorial, right? Lambda to the 4, 5 factorial, 3 factorial, 2 factorial, lambda to the 3, 5 factorial, 2 factorial, 3 factorial, lambda to the second, 5 factorial, 4 factorial, lambda to the 1 plus 1. So this is lambda to the 5th plus, this is 5 lambda to the 4. This is 5 factorial. 10. 10 lambda to the 3, 10 lambda to the second, 5 lambda to the 1 plus 1. So nice differential equation. So I'll give you as another homework. So we have L is dx5, d5, dx4, d4, 10, dx3, d3, 5, dx2, no, 10, 2, 5, dx, d1. So L is the ordinary differential equation, 5th order, linear ODE. Then we know the solution, right? Solution will be exponential minus x, x exponential minus x, x squared exponential minus x, x cubed exponential minus x, x4 exponential minus x. So show that they are solutions. This is another homework. You have to differentiate 5 times. And I think that can be a good practice for you to review your previous calculus, how to differentiate functions. Maybe it may take 1 hour. So total homeworks I gave you today maybe take 2 hours. It's a good practice. And I'm going to move to another topic, but before I move on, if there is any questions, maybe this is the time. So everybody understand what we are doing now? You're following? Completely okay with you? Yes? Okay. So next case is called the equidimensional case. Here up to here. Squeeze is up to. That means the equidimensional case will not be covered for fields. Good news, right? So first order differential equation, and the ordinary differential equation is constant coefficient. And of course, you need to handle the logarithmic derivatives. So those are the subject of quiz. And remember that we also covered the polar decomposition, right? Polar decomposition, which was not covered by previous quiz. So this quiz will cover polar decomposition plus first order ODE and the differential equations with the constant coefficient, but not the equidimensional case. I'm going to leave for the next quiz. Name Equidimensional differential operator. If n L yx equal to 0 is equidimensional ODE. So this time the coefficient is actually a function of x. So it looks very complicated. And the goal is to transform this equation into something easier, something we can handle, such as ODE with constant coefficient. So, for example, we can try yx is actually some function of zx. So we're going to introduce some intermediate variable zx. And set z as ln x. For example, are you following me? So we have a new type of a differential equation called equidimensional differential equation. And so the derivative is matched by x to the n. The derivative of x to the n minus 1 is matched by n minus 1. So their dimensions are the same. So that's the reason why it's called equidimensional differential operator. And in case of a differential equation, it is called equidimensional ODE. Battery seems to be running out. So we are going to transform this equation into something more easier. So let's try. So even though we learned that, so for example, dx, dy, cx is dz, dy, cx, dx, dzx, right? Chain rule. We learned this. But this dx, dz is dx, d ln x is 1 over x. So this is 1 over x, dz, dy. x dx dy is same as dz dy. We differentiate once more. Dx squared d squared y. So we first differentiate this part, minus 1 over x squared. Plus 1 over x, dz squared, d squared y, d squared dx dz. So that is minus x squared, dz dy, plus x squared, dz squared, d squared y. So we can set x squared, dx squared, d squared y, z is same as dz squared, d squared y minus dz dy. So actually you can put this way, dz d minus 1 y. So we can continue. So if we continue this, xn dxn dn y will be something like this. dz d minus 1, dz d minus 2, blah blah blah, dz d minus n plus 1 y. Right? So our differential operator actually can transform into the following. It's just the application of chain rule, then copy, right? So isn't it fun to do this? Right? You don't think it's fun? Okay, so today, but since the time it's out L. Oh. A0 xn dxn dn y a n y can be transformed into the following equation: a0 dzd dzd minus 1 dzd minus n plus 1 y plus a1 dzd dzd minus 1 dzd minus n plus 2y an y. So highest order will be n times, right? This will be nth order. So somehow if we rearrange these terms, we can have the following. You can have the following: b0 dzn dn y plus p1 dzn minus 1 y pn y, right? So you can transform this equation into the z. So for example, if L is given by x squared, dx squared, ax dxd plus b, then L yx is x squared, dx squared, d squared y, plus ax dx dy plus by. But by setting zx into ln x, we have the transform into dz minus 1y, right? A dz dy plus by. So that is d squared y plus a minus 1 dz dy plus by. If this is 0, then we can try what? Try a solution can be y equal exponential lambda z, right? So, for example, lambda square plus a minus 1 lambda plus b exponential lambda z equal to 0. So let's consider the easiest case, a equal to 4, 3, b equal 2. Then what do we have? For example, then in this case we have lambda square plus 3 lambda plus 2 exponential lambda z is equal to 0. So lambda is minus 1 minus 2, right? So we have more room here. So y exponential minus z or y equal minus 2z are solutions, right? But what is exponential minus z is what? Exponential ln x, right? Is exponential ln 1 over x, and this is actually 1 over x, right? Likewise, exponential minus 2z is exponential ln 1 over x squared is x squared. You can use the fact that a is exponential ln a, right? Use this. Okay, I think I covered too much material today, so I'm going to reduce the amount, the material you need to study for the quiz. So I'm going back. Leave this for the next time. And I'm thinking about I'm going a little too fast. Maybe stop today. What do you think? So I'll stop a little earlier today. 이게 같으면은 1이고 다르면 0이잖아. 그러니까 이게 i로 남아야지. 얘가 같으면 다른 다 없어지잖아. 근데 k가 같을 때만 살아남는 거니까 이것도 j로 바뀌어있어. 썸이 있어야 될 거예요. 썸이 있잖아. 썸도 k가 있거든. 썸이 있는데 이 썸은 이게 j가 k랑 같을 때만 k가 j랑 같을 때만 살아남잖아요. 그러니까 여기서 람다 j n가 나오는 거지. 요 썸 때문에.
이게 여기에서 여기까지 이렇게 되는 거예요?
그렇죠. 이 썸이 여기까지 들어가야지.
아, 요거랑 요거 이렇게 내죠?
네, 그렇죠. 네, 이해가요?
그럼 이게 또 이거 IJ인 거예요?
그렇죠. 그 델타 i들이 맞아요.
이게 여기서 여기.
그러니까 이것도 이제 NINJ잖아. 그죠? 람다 J잖아. 같으면 1, 다르면 0. 그죠? 근데 같으면 이것도 람다 J가 같으면 없어지잖아. 없으면 0이고. 없으면 어차피 0이고. 네. 지금 너 좀 빨라지는 거.
오늘 맞는다.
어?